Well, hello and welcome to a video about mixtures and how to calculate mass fraction, mole fraction, and some examples that might help you in your engineering problem solving. So let's go ahead and get started. So we're going to cover, well, what is mass fraction? What is mole fraction? And how are they similar and different? So there we go. How are they similar and different? And then some example problems. And what I'd like to do is point out what are some key solution approaches to both dealing with mass fraction problems and dealing with mole fraction problems. So first, let's have a crash course, and I'll go through this as quickly as I can, but it's a reminder of your textbook and class material related to mixtures. So what's a mass fraction and mole fraction? Well, these apply to a mixture of constituents. And for chapter 12, these are going to be mixtures of ideal gases. But remember, mixtures can come in all types of different constituents and phases. For example, salt water is a very commonly observed mixture of water and sodium chloride. But for our purposes for chapter 12, we're going to be looking at ideal gas mixtures. Okay, so first, a review of what is mass fraction. And so the nomenclature here is MF, mass fraction sub I. So each constituent, I, will have its own mass fraction. And then, of course, recognize that if you sum up all the mass fractions in a mixture, you're going to get 1.0 or 100%. That makes good common sense. Well, it's a mole fraction. So in terms of nomenclature, mole fraction is represented by Y sub I for each constituent. And the same idea, if you add up all the mole fractions, you're going to get 1.0 or 100%. Let's review a little bit about your freshman chemistry or even high school chemistry. The volume fraction for each constituent is exactly equal to the mole fraction. Okay. Now, that has to do with the way we model our homogeneous mixture. So, for example, if you read in a problem, a volumetric analysis of a mixture results in nitrogen at 60%, oxygen at 30%, and CO2, carbon dioxide, at 10%. Well, here's what that means. You can just immediately write down Y of N2 is 0.6, Y of O2, 0.3, and Y of CO2 is 0.1. Those are the mole fractions. Volumetric analysis, same as mole fraction. Now, a little review of your textbook material that we're covering in chapter 12. Really want to chase you to look at your textbook material, particularly section 12.2, regarding Dalton's model for ideal gas mixtures. And in that section, we introduced the idea of partial pressures. And you could say it's sort of a theoretical model, and that's okay to think of that way. Partial pressure is a term derived from Dalton's model for gas mixture, and also recognize that partial pressure is a property of each individual constituent within this homogeneous ideal gas mixture. And so the most important equations or fundamentals in section 12.2, equation 12.12, it's a little small, P sub I equals Y sub I times P. What does that mean in words? In words, the partial pressure of each constituent equals its mole fraction times P, which is the pressure of the system. Now, so when I was learning this, I didn't use just P. I would write down P sub sys, P of the system, and that helped keep me straight about the system pressure compared to the partial pressures. That helped me. Now, equation 12.13, which is another fundamental, is that the system pressure P sys, equals the sum of all the partial pressures. Okay, what does it mean in words? The system pressure equals the sum of all the partial pressures of all the constituents. That's a pretty easy concept, but you do have to You have to learn that. You have to keep that in your mind. Partial pressures, what's the purpose of partial pressures? The sum of them is going to equal the system pressure. So if you have the mole fraction and you have the system pressure, that's very common, then you can calculate all of the partial pressures of each constituent. Little reminder about a system. Okay, and so we'll go all the way back to the first week of class. A system can either be a closed system or an open system. And when you read an engineering problem, that's like step zero, in addition to drawing a sketch. Do I have an open system or a closed system? Quick review: closed system, fixed mass, and for a mixture, we've got two or more constituents homogeneously mixed in that fixed mass. The system pressure is described as P, or in my world, P system. And recognize, we just covered some of the partial pressures equals the system pressure. Really works for a closed system. Let's say you have an engineering problem that's an open system. How do we characterize an open system compared to a closed system? We look for keywords that indicates we've got inlet and or outlet flow streams. In steady state, steady flow models, which is most of our engineering problems, the sum of the inflow streams equals the sum of the outflow stream mass flow rates. Now, each stream might be a single constituent. You might have nitrogen coming in one stream and oxygen coming in a different stream, and they're mixing in a vessel, and there's one outlet, which would be the homogeneous mixture, and that would be a mixture of constituents. So that's an idea for an open system. And then recognize that partial pressures apply to each stream, okay, based on the constituents' mole fractions, what's going on with the stream, and each stream's measured pressure. And I'll try to give a little example of that if that's too much. But I think you can visualize the little example I gave. A steady state, steady flow situation where nitrogen's coming in one stream, well, it's one constituent. Oxygen coming in another stream, that's just one constituent coming in. But within a vessel, these two are being mixed together, and the outflow, now the sum of the mass flows would be the sum of the inflows, is going to be a mixture of nitrogen and oxygen with, say, some mole fraction associated with them. Let's do some practice reading real homework problems. Okay. The analysis on a mass basis of a gas mixture at 40 degrees F is blah, 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 blah. And you're asked to find different things associated with that. Well, when you quickly read the problem, mass basis, well, that means the mass fractions are given. You simply look at the problem statement and write down mass fraction of CO2 is 0.6. Mass fraction of carbon monoxide is 0.25, mass fraction of oxygen 0.15. Okay, that's the mixture. You could imagine that it's held within a vessel and then move ahead to work the problem. Next problem. A mixture of 5 kilograms of hydrogen and 4 kilograms of oxygen is compressed in a piston and cylinder. Blah, 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 and you're asked to find a couple of things. Okay, a quick reading. Okay, do I have the mole fraction or the mass fraction? Could I figure it out? Of course, the answer would be yes. When you read the problem, you're given the masses of each constituent. So therefore, applying a little common sense, the total mass in this piston and cylinder closed system would be 9 kilograms. And so you can immediately calculate the mass fractions. Mass fraction of hydrogen, 5/9, and mass fraction of oxygen, 4/9. Again, applying some common sense to reading a homework problem. All right, let's look at problem 3. It says, natural gas has a molar analysis of 60% methane and 40% ethane. That's a good model for natural gas. Okay, well, you look at the key words, molar analysis. Well, that says then, of course, that the mole fractions are given in the problem statement. CH4 mole fraction, 60% or 0.6, and ethane 40% C2H6 is the mole fraction. So all the key here is carefully read the words of the problem, and pretty quickly for these mixtures, chapter 12 problems, you're going to understand what's given. Is the mass fraction given, or is the mole fraction given? Okay, problem 4. An open system, argon, has a mass flow rate of 1 kilogram per second entering an insulated vessel. Okay. Also entering the vessel is carbon dioxide entering it as a separate stream, but its mass flow rate is known. Okay. And so, and the sketch is shown too. What can we determine from this sketch? 2 inflows, argon and carbon dioxide, steady state, 1 outflow. So that tells me that the mass flow rate at 3 has got to sum up to m.1 plus m.2. Another thing is these are mixing to come up with a homogeneous mixture of argon and CO2. So I've got to have to worry about this mixture only at state 3, two single constituents inflow. Open system, steady state, steady flow, 2 inlets and 1 outlet, and then you're pretty well on your way in solving this problem. Let's talk a little bit more about state 3. How will you handle state 3? Well, let's see. Can you figure out the mass fraction at state 3? I think you can from the given information and your common sense and your experience so far with steady state, steady flow, continuity equation. What's the mass flow rate at state 3? It's 1.5 kilograms per second by observation. How much CO2 is flowing out in state 3? Well, 0.5 kilograms per second are flowing out. So the mass fraction of CO2 is 0.5 over 1.5. Do the same thing for argon. What's flowing in is 1 kilogram per second. That must exactly equal what's going out. So the mass fraction of argon is 1 over 1.5. So, okay, so in other words, what's given in the problem? Basically, the mass fractions at state 3 are given. Okay, another thing to observe, the system pressure at state 3 is given. The measured pressure at state 3 is 1 bar or 100 kPa. That's going to be used in the problem. Now, if you're asked to find the partial pressures at state 3, is that given? And the answer is no. The partial pressures at state 3 depend on the mole fractions, not the mass fractions. So recognize if, as you work through this problem, you're going to have to take the mole fractions and figure out, you're going to have to take the mass fractions that you've got and figure out the mole fractions in order to get the partial pressures. Okay, and one last observation is that partial pressure is not involved with state 1 and state 2 because each of these inflows are not mixtures, they're just single constituent inflows. Let's move to another example problem reading. Problem on a 5th one, it says, I've got to move my Zoom menu, so just pardon me a second. Here we go. A gaseous fuel with a volumetric analysis of 60% CH4, 30% hydrogen, and 10% nitrogen is burned to completion. You're going to be getting into chapter 13 for this. But do you see that the mole fractions for this problem are given in the problem? Mole fraction, CH4, 0.6. Hydrogen 0.3 and nitrogen mole fraction 0.1 because it says volumetric analysis. So that's kind of critical to recognize. Volumetric analysis means mole fraction is given. Okay, one last reading problem. Let's say you've got a real honest to goodness study and you're trying to find out more about the natural gas composition of natural gas, a chemical composition of natural gas, and you go to Google and you do a Google search on natural gas chemical composition. I did just that, and here's the link to the return for that. And I get a pretty nice table that gives me some ranges of a bunch of compounds that are commonly found in natural gas, what we buy commercially, natural gas from the street. Okay, bunch of different compounds, bunch of different symbols, and then it says percent of in natural gas. And that's all it says. It says the percent basis for this Google search is not stated. So let me just give you a little practical advice. When you're doing Google search for gas mixtures, and the percent is given, but it's not stated, commonly that means a volumetric basis analysis, or in other words, these would be mole fraction ranges. So anyway, that's just a little side trip for when you're doing Google searches on chemical compositions of various gaseous mixtures. Be prepared for that. We're still in our little bit of our crash course. Determine R of a mixture and CP of the mixture. You're going to be doing that all the time in your homework problem solving. Let's refresh. What are the units of R and C sub P? Okay, R and C sub P. Kilojoules per kilogram degree K, or BTUs per pound mass degree R. Okay. Why would we use R of a mixture? Why would we do that? Well, if we have a mixture and we're asked to calculate the volume or the specific volume, man, we need that R of the mixture. That's the easiest way to calculate volume or specific volume using the ideal gas equation of state. PV equals MRT for a closed system, or P times little v equals RT for either an open or closed system. Okay. That's why we would need to use R mixture, okay? And it's a simple matter to calculate R for a mixture, recognizing that the mixture ideal gas constant equals the sum of the mass fraction of each constituent times R for each constituent. Same thing for C sub P, sum of the mass fractions times C sub P for each constituent. That's the way you get R and CP for a mixture. Another little reminder, what's R for any ideal gas? How do you, if you're in a test situation, oh my God, I'm not given R for nitrogen, what do? I've got to remember that R is R bar over the molecular weight for any ideal gas. So for any constituent, nitrogen, oxygen, CO, CO2, R sub I is R bar over the molecular weight of I for the constituent. What's R bar? Can I remember that? I hope that you've got committed to memory at least the first two. R bar is 8.314 kilojoules per kilomole degree K, and R bar also equals 1,545 foot-pounds force per pound mole degree R. And then you're in good shape to start solving these problems. I think that's the end of our crash course. It is. Let's do example problem number 1. And I'm trying to mimic example 12.1 in your textbook. So this doesn't replace what you're doing in your textbook work. Example problem 1, a closed system is comprised of 3 ideal gases. It says a volumetric analysis reveals CO2 60%, CO 25%, and oxygen 15%. And the problem is determine the mass fractions. Should be pretty easy. Here's what we do. I just want to work you through the steps to be sure you see how to do this. Set yourself up with pencil and paper, a table, constituent. Write down your 3 constituents. The mole fraction, which is given. So we've got to determine the mass fraction given the mole fraction. Write down those numbers. What's given? Next, you're going to write down the molecular weights for each constituent. Then you've got a column heading that says the mass in kilograms of each constituent in 1 kilomole. I'll show you how to get that. And then finally, you'll be able to determine the mass fraction. So remember, for this problem, it said volumetric analysis. That meant that the mole fractions are given. Next step, write down the molecular weights. You need to know how to, in the back of your book, how to get these molecular weights if you have not committed these to your memory. Hopefully, after freshman chemistry, you will have committed these to your memory. The next column, the mass in kilograms in 1 kilomole of mixture. Here's the way you do this. Multiply the mole fraction by the molecular weight and write that right down. 44 times 0.6, et cetera, et cetera. That's what you do. Now let's check units. Instead of just blindly doing this because the video says to do it, let's check our units. Check multiplying the mole fraction, kilomoles of I, over kilomoles of mixture. That's the mole fraction, isn't it? Times molecular weight, kilograms per kilomole. So if you do that algebra, you get kilograms of constituent I per kilomole of mixture. That's why you multiply these two columns together. Okay, there's the math. Okay. Next thing we do is we sum those numbers. We sum all the masses up to get the sum of the masses. So that's the kilograms mass in 1 kilomole of mixture. All right, what do we do? Okay, boom. There's our math. There's the total math. And is it pretty obvious what the next step is? The mass fraction is going to be this mass divided by the total mass. Mass fraction CO2, this mass over the total mass, et cetera, et cetera. Okay, so we've done the math. Divide each mass by total mass to get the mass fraction, and you're done with the homework problem. Okay, let's see. Let's recap what we just did. We need to sum up our two mole fraction and mass fraction columns. Do they add up to 100%? Yes, that's good. Okay, and also observe that these numbers do not equal each other. That's good. Okay. And they may be wildly different depending on the molecular weight, the relative molecular weights of your various substances. So for example, if you have hydrogen, molecular weight of 2, you're going to find that the mass fractions are dramatically different than the mole fractions. These turn out to be around the same order of magnitude. So the fractions are around the same order of magnitude. Okay, hope you got that. Let's move on to the next example problem. Trying to mimic example problem 12.2 in your textbook. Maybe a little different complexity, okay? Closed system comprised of 3 ideal gases containing 6 kilograms of CO2, 3.5 kilograms of CO, carbon monoxide, and 2.5 kilograms of oxygen. Do you see that the mass fraction is basically given? Okay, I hope so. And the problem is determine the mole fractions. So I hope you immediately see that you have the ability to calculate the mass fractions on your own. Okay, fully disclosed. The mass of the system is 12 kilograms. So you immediately calculate out the mass fractions of the different constituents. You say, oh boy, I might get partial credit on a quiz for this. You'll get a little partial credit on a quiz for this, but not much. Next thing is to set up your table. Again, it's not identical, but it's very similar. Write down your constituents. Write down your mass fractions, MF sub I. Okay. Next, write down the molecular weights. Again, okay. You're going to, in this column, you're going to calculate the number of kilomoles in 1 kilogram of mixture. I'll show you how to do that. And then finally, that'll be enough to calculate the mole fraction, and you'll be done. Tried and true, write down the molecular weights. I'm copying that from the previous example. The next step is to divide each mass fraction by the molecular weight. Okay, and so I've done that. You see, I've done that on my table. And instead of just blindly doing it, let's check units. Divide mass fraction, divide by molecular weight. So we've got kilograms of constituent I divided by kilograms of mixture divided by kilograms of constituent I per kilomole of constituent I. So that means, so if we look and do the algebra a little tougher, we get kilomoles of each constituent per kilogram of mixture, kilomoles per kilogram of mixture. That's the way we get this column entries. Okay, so I've shown that. Let's do the math. Okay. There's the math is done. We're going to add those numbers up to get the total number of moles for all the constituents. Now, this is slightly different than your textbook. Textbook said we're going to use 100 moles. I find that to be confusing. So whichever works for you, whichever method fits your understanding the best, use that. Okay. So mine's a little different than the textbook, but we're going to get numerically the same result. Okay. We've summed all of the moles together. Mole fraction, pretty obvious. I'm going to take each number of moles divided by the total number of moles to get the mole fraction. Okay, there you go. Check our work. We're going to sum up both columns, mass fractions and mole fractions. They both add up to 100%. Great. And also, we're going to observe that the mole fractions do not equal the mass fractions. And that's relief. Okay. All right. Woo. We've been through 2 example problems. We've got a couple more to go. Example problem 3 is a tried and true ideal gas problem that, and here we go. It's a problem that you should be able to solve in your sleep because it's a reprise of a problem that you probably had in the 3rd week of your thermo class. Wow. And so there's a reason I want to do this reprise. One is final exam prep. I had a problem in 1973, I had a problem very similar to this on my final exam it was 1st quarter thermo at the time. And the professor gave this easy problem at the end of the semester for a reason, okay? And that was, if a student can't do this problem nearly perfectly, that student probably needs to repeat thermo. So please be aware in your preparation for your final exam, prepare yourself to get an easy problem and be prepared to do it very, very well. So let's look at this problem. An ideal gas, doesn't say anything about a mixture, just says an ideal gas with a molecular weight of 28.5 kilograms per kilomole is contained in a rigid vessel with a volume of 4 cubic meters. Yeah. There's a sketch coming in your mind. The gas is initially at a temperature of 25 degrees C and a pressure of 100 kPa. The ideal gas is heated until the temperature becomes 35 degrees C. Heat it up a little bit. Here's the problem. Determine the mass of the ideal gas in the vessel. Determine the final pressure in the vessel and the amount of heat added during the process. Notice here, it doesn't say part A, part B, part C. It's all in one sentence. And also given the specific heat of the ideal gas is described by CV bar equals 1.5 R bar. That's important information. How will we solve this problem? I hope that I've dwelled long enough on this problem that you've got a picture in your mind of where to go from here. Where do we go from here? Let's start with a sketch. Closed system, rigid tank. I'm going to substance, ideal gas, known molecular weight. I'm showing heat in. Work out. I'm showing that as 0 because on my pressure volume diagram, which I also drew, closed system, no change in volume, dV is 0. Work out equals 0. So that gives me a path in my mind. That gives me a path forward to find the heat added, Qn, first law. Okay. How about our steps? This is our given information. I know I'm going to need R, so R is R bar over the molecular weight. I better remember what R bar is. I've got the molecular weight. CV is 1.5 times R bar divided by the molecular weight. I'll be able to get that. Here's all my given information. I remember to transform temperature in degrees C into absolute temperature. And then what am I going to do? Notice that I haven't put pencil to paper with a calculator yet at all. I'm going to write out the ideal gas equation of state is used to determine the mass. M is equal to P1V1 over RT1. Everything is known on the right-hand side. I'll also use the ideal gas equation of state to solve for P2. I just found the mass. So P2 is mRT2 over V2. Wow. 2/3 of the way through. Huge amount of partial credit. Finally, the third thing, we're going to use the first law for a closed system to determine the heat added. let's see, we might write down no potential energy change, no kinetic energy change, so that Qn minus work out, that's 0, equals capital U2 minus capital U1. Well, that's M, got that, times little u2 minus little u1. Small temperature change, only 10 degrees C. So we're going to, we don't have any other information regarding specific heat. So we're going to hold it constant. So mCV times delta T is going to be the change in internal energy. Simple as that. Now let's do the math. We can do the math on one slide. Wow. Here's our calculation, written down information, given information in the yellow. Calculate R and CV in kilojoules per kilogram degree K. R is R bar of the molecular weight. I write down the absolute temperatures. I write down my given information. Pressure and volume is constant. V1 equals V2. Ideal gas equation of state, define the mass, 4.6 kilograms. Ideal gas equation of state, define P2, 104 kPa. Darn it, I didn't write my units down there. Sorry about that. Okay. And then first law, Qn mCV times delta T, 20 kilojoules. Simple as that. Should be able to do it in your sleep. Okay. So I hope that maybe gives you a little wake-up call for final exam prep. Now let's look at the next example. Very similar to example problem 4, except a mixture. Okay, so we'll read through it. An ideal gas mixture consists of 3 constituents. The analysis performed on a volume basis reveals N2 is 60%, oxygen 35%, and the remainder is CO2. The mixture is contained in a rigid vessel, sounds familiar, with a volume of 4 cubic meters. Mixture is initially at 25 degrees C and a pressure of 100 kPa. Ideal gas heated until the temperature becomes 35 C. And then finally, the question, determine the mass of the mixture in the vessel, the final pressure, and the amount of heat added during the process. Wow. So numerically, it's not going to be an exact duplicate of the previous example, but I hope you see that this problem is extraordinarily similar to the previous example problem. I hope you see it. Okay, so let's look at the solution for this. Let's start with a sketch and plan the work, okay? Identical vessel, identical sketch of the vessel, rigid tank, identical pressure volume diagram, okay? We look ahead in our mind and think, what am I going to do? Well, I am going to use the ideal gas equation, so I'm going to need R for the mixture. Okay, so let's see. R for the mixture. I need the mass fractions. So that's going to be step 1. Get the mass fractions, although the mole fractions are given in the problem. Okay. But I think you see the path forward. Okay, so to get R for the mixture and CV for the mixture, you need the mass fractions. But you can get, if you're doing a final exam, remember, write down your fundamentals first to get maximum partial credit. Okay, so look at this. This is a screenshot, a copy and paste text box of the previous, near copy and paste of the previous problem. M is P1V1 over R mix T1. P2 is M, just found it, R mix T2 over V2. I need R mix, okay? First law, Qn minus W out, that's 0. So capital U2 minus capital U1 equals M, little u2 minus u1. Okay, that's going to equal M times CV delta T. I need CV mix. You can write all this stuff down before you put pencil to paper and with your calculator. Okay. Write these down to gain partial credit. Okay, now let's do the calculator work. Let's get the mass fractions. This is a reprise of example problem, let's say, I can't 1 or 2, I can't remember now. Given the mole fraction, find the mass fraction. So I'm going to write down my molecular weights. I'm going to write down my mole fractions. Okay, I'm going to multiply those two together. Okay, there's the numbers. Okay, I add these up to get 30.2, and my mass fractions fall right out. Now, let's see, what's different than my previous example problem? Well, all I did was, I see that as I solved the problem, I wrote down my molecular weights first and then my mole fraction second. So it doesn't really matter. These are identical as long as you do the math correctly by multiplying these two together to get kilograms per kilomole of mixture. So I've got my mass fractions now. Next step, I need to get R mix and CV mix, all right? R mix, easy. I remember R bar, and I've got the molecular weights of the three constituents, so R falls right out, that's easy. CV, I need to look up CV as a constant for each of the constituents. I go to table A20 and simply get a representative temperature. I picked 300, and I wrote them down in my table with my mass fractions that I just got. And so calculator work, it's easy now to calculate R the mix and CV the mix. Just multiply each mass fraction and each C sub V together to get R and CV of the mixture. Now we can do the math easily. It is a reprise of what we just did in the previous problem that you can do in your sleep. Use absolute temperatures, use the ideal gas equation of state to find the mass. This is a slightly different example problem, so we get a different numerical result. 4.9 kilograms. P2, darn it, I still didn't write out my units for P2 of kPa, okay? 104, okay? And then Qn, kilojoules, 34.4 kilojoules heat added. And so that falls right out. So do you see that these mixture problems can be very similar to problems that you've done in the third week of class? And so now we have reached the recap for the video. So mass fraction, what do we remember about that? Commonly used for continuity equations, let's say open systems, and first law applications. So to determine R of a mixture, CP of a mixture, CV of a mixture, you're using mass fractions, okay? Mole fractions, same as the commonly used percent volumetric analysis. So when you're reading a problem, recognize that the mole fraction is given to you if you see the word volumetric analysis. Also, mole fractions are used to determine partial pressures. So if you're asked to find partial pressures, or if you need partial pressures in various mixture problems, that's where you're using mole fraction, okay? It is simple. Once you know the recipe to convert between mole fraction and mass fraction, you've got to remember how to set up those tables, or if you're using a formula sheet in a test situation, write down a little example for those and recognize the two tables are different depending on what you start with and what you need to end with, okay? And then finally in yellow, a big takeaway I hope from this video is that ideal gas problem solving is similar for just one given ideal gas and very similar for homogeneous mixtures of ideal gases. So I hope that I pointed out those similarities in the example problems I gave. So that is it. I hope that that helps clear up maybe some questions that you might have had regarding mole fraction and mass fraction. I hope it helps you prepare for your final exam because we want all of you to perform well in your test and exam and quiz situations. Good luck with all that. And remember, the more you practice solving these problems, the better you'll be in performing on quizzes, tests, and exams.